Yes, so as I said, we'll start with some problems. So we'll do 3 problems today. Okay. And let me just present them as problems and we can think, and then we can look at how they relate to the ideas we have been looking at. So that's problem number 1 of the day. Okay. You guys can think while I write as slightly wordy. Okay. So we have the following. We have a volleyball net, football net, whatever, a volleyball net. Okay. So it is it's a rectangular net, right? So net has the form of a rectangular lattice is what it is called, but you can understand it's a net. Something, okay, a net. That is, and the dimensions with dimensions as 50 by 600. Dimensions is 50 by 600. So this is what it given. Now the question is, what is the, so when we play, right, some of the strings get broken. Okay, some of the small unit strings get broken. So what is the question is, what is the maximum number? So it's like an optimization question. What's the maximum number of unit strings? So unit strings, you can understand the smallest pieces. Unit strings can break. Okay, can break. What's the maximum number of unit strings that can break before the net falls apart? One second, someone is joining. Before the net falls apart. So this is some simple contest question. We'll see how we can do this. Let's think about this. Yes, so it is just a rectangular net, right? So you have, if you have seen, you have 2 poles. Poles are not important here, but then you have a net, right? And obviously net means what? It will look something like this. And what I mean by unit squares is, sorry, unit strings. Unit squares are also there, but what I mean is unit strings. You see, between these 2 red points, the piece, the part, that is a unit string. And obviously you can understand this is a unit string, this is a unit string, and so on. So how many of them can we afford to break in the best situation so that the net still is in one piece? Unit strings. Yes, right. So that's a very good start. Okay, let's see where we can take it. Let's see if others can also build on it. That's right. So we have already started modeling it as a graph. Okay, so each edge or the edges, see edges, you can understand these are the points, sorry, the lines in our graph. These are also called edges. Obviously, you know, edges are the unit strings. Okay, and falls apart obviously means, you know, it means gets disconnected. The vertices of our graph are obviously the meeting points of the unit strings. So how many can we afford to remove? In the best case, okay? In the best case. Okay, before we do this, can anybody first say what is a minimum? That is much easier. N, where is the N? No. What is the minimum? No. So read the question. Okay, let me first read it myself. Maybe I framed it wrong. So my question is, what is the minimum number of unit strings that can break before the net falls apart? Yeah. What's minimum number of strings that need to break? No, let's think about this more carefully. 3. Will 3 be enough? Which 3? Like, for example, you mean, yeah, that's right. This, like this, right? Would you call this falling apart? Yeah, they are, no, but, but we will call this falling apart because this net is no more a net that can be used, right? Maybe, I don't know, because the ball can pass through this. So there is a slight, yeah, so there is a slight, okay, just give me 1 second, the charger. Yeah. So there is a certain, the way it is framed. 1 minute. Plug in the charger. No, it will remain connected. Oh, one string is not enough, but okay, let's just make sense of this falling apart, right? The question is falling apart the same as getting disconnected, right? So obviously falling apart, let's make this clear. So there's a slight problem. Falling apart definitely implies that it gets disconnected. The net falls apart, it means it gets disconnected. But what would falling apart really mean? Falling apart would mean then that you have to either remove, if we don't think about it graph theoretically, if we don't think about a graph theoretically and just physically think about this, then what would falling apart mean? Yes, so that has to be the criteria, right? So then it's a very simple problem, right? Then it's a very simple problem, right? Because then obviously you would prefer that you um, yeah. So in that case, okay, let's just think. Then in that case, what will the maximum be if we take the physical meaning of falling apart? But is that the maximum? Can we do better? That's right. Yes, right. So that's a very simple thing then. Yeah. Is it clear with everyone, right? That's a very simple thing. If we take the physical meaning of falling apart, then obviously it's 50 it's 50. Right? Then it's 50. So then that's very simple. So let's not take that meaning. Let's take this to be equivalent to disconnected, or rather, yeah, getting disconnected. Why? So what I'm done, disconnected means that as a graph, which means that not all the points are connected anymore. Or means you can't go from one point to the. There will be some points. There will be a pair of points which you cannot reach from one to the other. Then you know, no, that's right. But also, Yeah, one second. And also the reason why I'm saying that this is right in the sense that why this makes more sense, because see, if you are going to remove, one second, if you are going to remove this and this, right, then this net is not usable anymore, right? I mean, you have a big gap. I mean, you have created it, it's not a legal net anymore, right? So yeah, so we should take falls apart to mean disconnected. In some sense, that has fallen apart. That net cannot be used, obviously. Okay. So yeah, so disconnected, and this is the same thing. Okay. So first, someone had some question. Can, or was saying something? Okay. Yes. Mm-hmm. No, it is disconnected. No, no, I'm not saying that. Someone had said that. So that was for the minimum. If we, right, if we take the minimum, then is this, yeah. So is this, so what is the question? It's not disconnected. That is right. Yes. Yes. So three is wrong. Four is the minimum. Yeah. Three will not work. We can obviously prove it. I mean, we can obviously see it more clearly. If you just take like this, you can still reach. So yeah, three will never work. But no, but let's see. Is there any other way in which we can make three work? Anyone has any idea? Okay, if okay, let me just make things more clear. What I'm asking now is the minimum. What is the minimum number first? What is the minimum? For four seems to be working, but can we do with less than four? Huh? Yes, absolutely. That's right. Yeah, only one is enough. So for this, if you remove this, then this is quite a useless net, right? And it's disconnected from our perspective, right? So yeah, one is enough, not even two. So the minimum is one. No. Okay, are you going to consider that? No, that is not an edge. No, that is not an edge. This is not an edge, right? The net, it gets separated, right? I don't think that be considered as an edge. That is not a string. That's a part of the pole. Yeah. So I think that was a question someone asked. Yes. So then this will get disconnected. Okay. One is enough. Okay. So then let's come back to our question. So the strings. This part is not a part of the string. It's a part of the pole, I would say. Yeah. So some ambiguity is there, but in any case, let's try to find the maximum. Yeah. No, even from a graph theoretic sense, right? If you remove this edge, then it's a disconnected graph, right? Because this red point is now disconnected. You can't reach it. Yeah. So these are very simple observations. Let's come back to the actual question. Mm-hmm. Mm-hmm. That is right. So if we want to, that's right. So if we want to maximize the number of strings that we can remove, okay, if we want to maximize the number of strings that, or the number of unit strings that we can remove and keep the graph connected, right? Then what essentially we are asking is what is the minimum number of edges we can keep, right? and that means that we are trying to make a tree, right? So a tree, yes, logically speaking, that is also, I think that will also give us the right answer, right? But then you have to actually prove that it will be the minimum. Yes, yeah, maybe something like that. So that idea can also work, but let us do it by the tree first. Okay, that idea can also work, I think. Yeah. So basically, what we are looking at, what we want is we want a tree as a subgraph. Okay. A subgraph here means that given these edges that are given the edges that are already there, we want to create a tree from here. Okay, and that tree, I should say a spanning tree. Okay, what I mean is spanning tree meaning that all the vertices should be included. Okay, a spanning tree. So for this, we need to obviously compute the number of vertices totally that we have. So how many vertices do we have? That's right. Yeah. So it is simply 51 times 601 because yeah, the dimension is 50. So it's 51 points and so on. So we have this many vertices. And how many edges do we have? Is that right? 50 into 600. No, but are you also counting this edge, this as an edge? That really depends on the convention, right? Yes, but it doesn't matter. You can see, I am also not, I don't know if what the question is actually asking, but you can manage it. You can write both the cases. Okay, if I'm counting that, then this. So yeah, so if we count that, then this is the number of edges. Doesn't matter. Doesn't matter. Okay, so how many can we remove? No, it's very clear. You have to just do some subtractions, right? Because in the end, you want, you can have, so these are the number of vertices. So you can have this many edges you can have. So how many you can remove is, you can understand, right? So this is the minimum number of edges that the tree will forward.